Oh, weird. I can just push the button. Oh, hell yeah. Awesome. Okay. Do that.
Does it get big?
No, we found a workaround. Okay, then I wonder what happens when we share the screen. Not sure File Explorer.
I want to be that weird guy at a party that will arm wrestle everybody.
So it's gonna work. Oh, thank goodness. We're just gonna turn the chat off. Hey. Like we are YouTube streaming legend is. Check out.
Is AJ still here or did he go?
He left.
Darn it. I would like you to, AJ's coming back, so when he's around,
Mhm.
could you get the nitrogen you need
Yes.
for tomorrow?
Yeah.
Like he's doing the presentation, I'd like him to, at least go with you so he knows where to go if he can do that.
Cool. I took them last time too, so.
Oh, good.
And we're getting
So-
this from chemistry, right?
Yeah.
Okay.
Another 10 liters is what was requested, so basically fill the thing up.
Okay.
If they can do that.
Okay.
And they'll need to be done sometime today.
Cool. Yeah, this is gonna work. And now I just have to click the button like I would normally for YouTube. So it's just the same, just different.
How much trouble would that be to set up in 132 for my next class?
Shouldn't be very difficult now that I
Okay.
know what I'm doing.
And let's see. AJ comes back for that, doesn't he?
Yes.
Okay, could you show him how so he could be doing that each time?
Yeah.
Okay. Hopefully we can get that dang Zoom link button working again.
Yeah.
Switch over to here. There should be that little square. I try to switch to over here.
Oh, I've spotlighted this video, so I have to spotlight that video. Yeah.
People from this class like that though.
Yeah.
Good luck.
Yep. Yeah, I now have to use custom live streaming service in this class. Because to go to meeting Zoom will obviously be weird. Probably confused.
So when we do the demo, are you gonna be able to?
Yeah, I can do that.
Okay, good morning, folks. It's about time to start. We're live on YouTube.
Yep.
Excellent. So where we left off yesterday, we were talking about pressure, which is force per unit area, in a fluid. And a fluid could either be a liquid or a gas. So we can talk about pressure in our atmosphere as depth in the atmosphere. As the deeper the atmosphere you go, the higher the pressure. And you probably felt your ears pop if you go over a mountain pass. And that's your body's attempt to have the same pressure inside your body as outside. But in a fluid, the pressure increases. So the pressure change is going to be the density of the fluid times G times H. So if you have a tank of water at a certain depth, the pressure will be, well, atmospheric pressure. That's the pressure above the water. And then as you go deeper in the water, it increases by an amount rho GH, where H is the depth. And typically we don't tend to consider the change in atmospheric pressure over, even tens of meters or so. In fact, there's very little change in atmospheric pressure, even on the order of a kilometer. There is a change, but it's small compared to the change we get even for just going a meter or so underneath water. But this pressure is the same at any depth. So like in this glass contraption here, at any given height, we have the same pressure inside. And you see that no matter what the shape is, we have the same fluid level. And as we tip it, you can see that that level stays horizontal. No matter how I tip it, no matter what the shape is.
Do you want to tip it one more time towards the owl camera?
Yeah, so see that level stays horizontal? And that pretty much water always seeks the same level at the same pressure. And as you go down in a fluid, even though this tube is thicker, we have the same pressure here at this elevation as we do over here in this narrower tube at the same elevation. So you can have the same pressure at the bottom of a very narrow water well that you would at the same depth inside a giant reservoir. Say, in American Falls Reservoir, if you go down 100 feet. Okay, how about 50 feet? 50 feet in American Falls Reservoir right near the dam. You get the same pressure at that depth of fluid as you would inside any of the wells that run those pivots. So those wells are, quite narrow, but also, quite deep. So it doesn't matter the size or shape of the reservoir, the size or shape of the container, you always get the same depth, the same pressure at the exact same depth. And to demonstrate that, Colton, you want to help me out with this one? I had the great wisdom of wearing button-up sleeves. And since Colton here has sleeves are easily rolled up, he can do this. What we have here is a manometer. And basically we have water in here with food coloring and saran wrap over a funnel connected to it. And so if I touch this very gently with my finger, applying some pressure on that saran wrap, you can see we have motion of the fluid there. Basically, the difference in height of the water columns indicates the difference in pressure. Okay, and so as we stick that in the tank, go ahead and just lower that in there. You see the pressure increases the deeper he goes. All the way down. And then right about in the middle of the tank, the pressure exerts the same force in all directions. It's unidirectional. So he's going to try his best to rotate this, keeping it about the same level. You'll try to keep where the center of that funnel is about the same. And you should see that no matter which direction that funnel is facing, the pressure force on that funnel, either from straight down or straight above or even from the side, is about the same.
Pretty low.
You're doing okay.
Okay.
Is that pretty clear here? I mean, he can't do a perfect job. It's really kind of hard. But keeping that about the same depth, no matter which direction he points the funnel, we get about the same pressure. Okay, thanks. And I've got another little toy here to try to bring about that point. This is just a 2-liter pop bottle filled with water. And if I were to stick a thumbtack in here, right there, I've got the lid on pretty tight. What will happen when I pull out that thumbtack? Anyone? Any predictions on what will happen when I pull that thumbtack out? If you're online, go ahead and speak up. Let's give the folks online a chance first.
I would think water would spill out just a little tiny bit.
You just keep pouring out?
Well, until it hit below it.
Okay. Did you have another prediction, sir?
Say maybe just like a little tiny bit, but I don't think it'll pour out of there.
Okay, you see it'll pour and then stop, but
Yeah.
not until it.
Yeah, might just, I think just a little bit of water will escape.
Okay, so why only just a little bit?
I'm not exactly sure. I think it has to do with, I mean, it's not able to draw any air.
Okay, so air can't go in, and so that's going to kind of limit how much water comes out.
Mm-hmm.
Okay, so who was that spoke up?
I want to say Mackenzie. Was that Mackenzie?
Miss Robbins? What's your name, sir?
Cooper Packham.
It was
Oh,
Alexis
actually, Alexis
Brunner.
Berger.
Who's Miss Brunger?
Yeah.
Okay, well, let's do the experiment. Let's find out. Oh, we get water, but look, it stopped. So the hole didn't seal because if I squeeze the bottle, we can squirt water out. What if I loosened up the lid?
And it
With-
would,
With your idea, that would mean that we can get water coming out again?
I think so.
Okay. Yes, we do. And if we twist that down, nope. Okay. Well, let's get another tack. Now I've got two in there. In fact, let's go ahead and toss one up there. And I'm thinking, yeah, even one down there. So if I pull out the white tack now, will we get any water coming out? What if I pulled out the red tack?
I think so.
Yes for the
It'll be
red?
Same reaction, more or less the same reaction as the blue one, as long as you pull out just only one.
Okay, let's pull out the red one. And it stops. Okay, put that back in. What if I pull the white one out now? You're shaking your head, nothing.
I don't think there's enough water to cause enough pressure to force any water out.
Nope, in fact, I saw a bubble. Air was sucked in when I pulled the white one out. Did anybody else see that? It's a pretty small bubble. So basically, if I pull out a bunch of these, you see we have air coming in the top hole, and the lower down in the fluid, the higher the pressure, and that shoots the water out farther. If I open up the lid, now we have water coming out all the holes, but clearly more so on the bottom. So the deeper you go in a fluid, the more pressure you get. And I did this with a group of elementary kids once. And I had a student say that, when I pulled out the bottom tack, that yeah, a little bit of water will come out, but then it's going to stop. And he made that prediction. And you can see that that was verified, but when asked why, he said, well, gravity only pulls stuff down, it doesn't pull stuff to the side. If you poked a hole in the bottom of that thing, it wouldn't stop. Water would just keep coming out. So if we try that, in fact, we did with that group of students. I said, okay, well, let's test that. In science, the laboratory is the ultimate authority. So we have one straight in the bottom, pull that out. Water comes out and eventually it stops for the same reason.
But it takes longer to stop.
It takes longer because it's deeper. Basically, what has to happen is, one way to think about this is the water level has to drop so that the pressure up here drops below atmospheric pressure. Water stops coming out a hole when the pressure at the hole is atmospheric pressure. If you have the same pressure inside the hole as outside the hole, there's no push to make the water go out. And granted, the pressure down here is greater than the pressure up here by an amount rho GH. The deeper you go in a fluid, the higher the pressure. But that means that the pressure up here, where we have just air in the top of the bottle, is lower than atmospheric. Because that water, by dropping, forced the air here to take up more space, and that lowered the pressure. So the pressure at these holes, when I open the very bottom one, once it stops, that tells you the pressure is equalized, and that's because we have the rho GH from that depth plus the pressure up here finally equaling atmospheric pressure. Does that make sense? That we actually have a pressure slightly lower than atmospheric pressure in the top of this bottle. Any questions on that point? Okay. It's actually a fun experiment to do at home and maybe share with your kids. It does create a little bit of a mess, but I think it's worth it. So, let's see. Let's talk about buoyancy. Something floats or something sinks if it's more or less dense than water. If it's more dense than what it's in, it'll sink. And if it's less dense than what it's in, it's going to float. And we can actually determine the buoyant force on an object. So if we have a big tank, and let's have a cube. So a cubic box in water, and let's say the sides are all A. And so if the length of each side is A, the area of each side is
A squared.
A squared. And the volume is,
A cubed.
okay? Okay, so let's say the bottom of this box is at depth H, and that means the top of this box is at depth H minus A. And so the pressure at this level is equal to atmospheric pressure plus rho G H minus A. And the pressure at this level is atmospheric pressure plus rho G H. The buoyant force on this object is the difference in pressure. We got pressure forces exerting on all sides of this box. And I tried to make the arrows here a little bit longer than here, and the arrow here a little bit longer than here. Not quite sure if I succeeded, but the pressure increases with depth. Call that pressure top, pressure on the sides, pressure on the bottom. And the pressure on the bottom is greater than the pressure on the top, and the pressures on the sides are kind of in between on average. But technically, the pressure on the side down near the bottom is higher than the pressure on the side near the top. So, but the pressures from all the sides cancel. So the pressure forces cancel on the sides. The difference in pressure between the top and bottom is what determines the buoyant force. So the net force on this box is going to be the pressure force on top, while the pressure, well, the force is pressure times area, because pressure is force per area. And so the net force on this is the pressure on the bottom times the area squared, well, times the area, minus pressure on the top times the area. And when we do that, atmospheric pressure just kind of cancels out, because in here we'll have like a P naught A squared and P naught A squared take the difference. So the difference in force is rho G H A squared minus rho G H minus A times A squared. And you can see that this whole term here cancels with the term that's multiplying by H over there. So we're just left with rho G A cubed.
What about the height?
Not important. It cancel. Cancel completely.
Even though there's a difference in the height?
And we get what's called Archimedes' principle. the buoyant force on an object is equal to the weight of the fluid it displaces. So we've got basically the density of water times G times the volume of that box. The density of water times the volume is the mass of water that's in that box, that would be in that box, in the same volume. Basically, the buoyant force is the weight of the fluid displaced. This is Archimedes' principle. And if the tale is to be believed, Archimedes was tasked with determining whether or not a gift to a local politician, a king, its basic was a crown. Was it solid gold or was it gold plated? And he was tasked with determining this without actually harming the thing, shaving off the gold to see if there was some other metal underneath. And thinking about it, it came to him that that this must be so. And so by looking at how much of a buoyant force would be on this crown, he could determine essentially its density. So by measuring its weight above water and then its weight within water, he could get a very accurate estimation of the volume of the thing, and knowing its weight, he can determine its density and compare that with the known density of gold. And supposedly he was he was in the baths at this point, the public baths, and this came to him and he shouted, "Eureka!" And he had to go and tell the king that he found a way to do it. And so he basically ran straight from the baths to the palace, buck naked. So that's at least the history story there. But this is Archimedes' principle, that the buoyant force is equal to the weight of the displaced fluid. And we talk about relative densities for determining whether or not something sinks or floats. Did I do the Coke Diet Coke float on the first day of class? I can't remember.
I don't believe so.
Could you grab a can of Coke and Diet Coke?
Yeah.
But something floats if it's less dense than what's around it, and it sinks if it's more dense. And we float in water because we're less dense than water. We have less stuff in the same space. The buoyant force on us can match our weight, unless you're a very lean sort of person. Most of us, me especially, can displace a lot more water than we actually weigh, and so we can float. Some people, if they have very little body fat on them, muscle tissue is more dense, they might have more difficulty floating, or maybe just the top of their head might be floating. Some people will actually sink if they're dense enough. But battleships float in water just fine, even though they're made of heavy armor plating. A lot of heavy metal on a battleship, but they float just fine because there's a whole lot of empty space inside. Overall, the density of a battleship is less than water. It has to be, or else it wouldn't float. And I've got another demonstration with this guy here. I have my own little boat. And you can see it doesn't sink very deep. Oh, we got the Coke and Diet Coke. Good. So here I've got a can of regular Coke. And it goes to the bottom. Can of Diet Coke. And it floats. Both cans have the same volume. They clearly don't have the same weight. That's because in the Diet Coke, you've got NutraSweet, which is a fairly low density fluid. While, actually, I think I can just let that sit there. It's fine. Has sugar water in it and is a fluid that's fairly dense. So what I have here is I have my own little boat. And let's say I have an anchor in this boat, a big brick. And this brick would clearly sink, right?
Oh, yes.
Actually, there's one other point I wanted to make here. In fact, you asked, well, where is the dependence on the depth? It cancels out. As you lower an object deeper and deeper into a fluid, what matters is the difference in pressure from the top surface on the top of the thing and on the bottom of the thing. That's what matters. The actual depth doesn't matter. As you lower something down, yeah, the pressure on the top increases, and the pressure on the bottom increases, but the difference in those pressure does not change as long as the density of the fluid does not change.
Okay.
So even in the ocean, there is very little change in density of the water as you go deeper. Eventually you'll get to much, well, not much higher, but measurably higher densities as you go deeper. There's actually more of a dependence on the density with temperature with water than the pressure, because water is actually pretty unsquishable stuff. It's very hard to squish water. That's why we use it in hydraulics. So there's very little change in the density with the depth in the water, unless you have significant temperature changes, because the temperature change will change the density of the water. And especially if you pass from one layer to another where you have a big temperature change, that's where you see a density change. But even in the ocean, you're not going to see much of a difference in density. And so the buoyant force will certainly pretty much be constant on something, irrelevant of its depth.
We had a question, Dr. Steve.
Yes, what's the question?
Is there a density change in salt water compared to fresh?
Well, salt water is more dense than fresh water. But again, even in the ocean, there's not much of a change in density with depth once you're talking about salt water, but there is changes in salinity. Like near a lake, near a river mouth, you've got fresh water coming in. That's going to be lower in density. So the fresh water will tend to stay on the top. And as the two mix, well, you're going to have a fluid that's a little bit in between the density of fresh water and seawater. And also in certain ocean currents, you'll have a change in salinity as well. So yes, salinity affects density. So salinity affects density, temperature affects density of seawater, but there's not much of a change in density with pressure. So basically, you'd have to go to a region where you have a different salinity or a different temperature to see a change in density. So as long as you're talking about the same sort of water, seawater or freshwater, there's really no change in the buoyant force on an object with depth because the density doesn't change. Okay, so let's get back to our brick here. So think of this as like a heavy anchor inside a small boat. And right now you see that the boat is displacing a lot more liquid than it was before. Basically, it's riding lower in the water. The water line is higher up on the boat than it was before I put that brick in there. If I put a second brick in, you can see it rests even lower.
Displacement has increased, which gives it more buoyancy.
Something else, I have a Sharpie here and a piece of tape. That's where the water level is in the fish tank. And you can see, if I put this in here and the boat displaces more water, the water level should rise. The water level should be above that mark now. Does you see that? Okay, now, here's the question. And if I take this brick out and instead throw it overboard, when I take the brick out, obviously, this water level will drop. But then as I put the brick in the water, it'll rise again. But will it rise to the same level? So that's the question. If I throw the anchor overboard, will the sea level rise or fall or stay the same? But we're not in ocean where we're riding this boat in, say, in our bathtub. Which reminds me of another thing that's kind of fun to point out. Can a battleship float in a bathtub if the bathtub is big enough? And the answer is yes. Because again, we have the same pressure, the same depth, regardless of whether or not that boat is in a gigantic ocean or a small reservoir or in a lock where there's very little water around the boat. Does that make sense? Because the pressure is the same at any depth, you can theoretically float a battleship in a bathtub if the bathtub was just a little bit larger on its inner dimension than the battleship is on its outer dimension. Okay, so this is one for the cards. Actually, why don't we do thumbs? Folks online, you can do thumbs up, thumbs down. on this one? Or can you do a thumbs down? I don't think you can do a thumbs down, can you? Or you can just type in up, down, or same. How's that? And so for people in the classroom, if you think when I put the water thing back in here, the water level will be higher than this mark, use a thumbs up. If you think the water level will be lower than this mark, do a thumbs down. Everything is the same, do this. Okay, I want to see what people think. Thumbs up, thumbs down. Online, just say up, down, or same. What are we seeing?
Mainly downs, one up.
Okay, could I get a volunteer to defend up, please?
Can you hear me?
Yes.
So I thought that because the brick is not completely submerged in the water where it's sitting in that container, I thought that when it's completely submerged, the water level would be higher.
Shelby, did you change your name?
It's Shelby Reynolds.
Okay, congratulations.
Thanks.
The Zoom link says Tillotson. That means you probably got married. Okay, so right now, if you look at this, the level of the water is below the top of the brick. And so since it's not fully submerged, we should see the water level go up when we put it in the water. Could I get a volunteer to defend why it's not going to change at all? Somebody who said same. We had several folks in the classroom say same. Anybody online?
There's one same.
Okay, somebody want to volunteer to defend why it should be the same? That was actually a far more common response than having the water level rise. Anyone? Okay, how about drop? Can someone defend why it's going to drop?
I'll give it a try.
Yes, please say so.
So I was just thinking that I know volume doesn't really matter in this situation, but with the brick dropping, the displacement of the water will be less because the tub will be up higher. And so that's why I thought that the water level would not rise quite as much.
Okay, so yeah, the water level will rise a little bit with the brick in there, but the tub displaces very little water by itself. But it displaces a lot of water with a brick in there. Well, let's do the experiment. Let's find out. Take the brick out. Clearly the water level dropped. Put the brick back in. Being careful not to drop it, that's why we have the string. And somebody dropped the brick once, and of course it broke the tank.
Oh no.
And the water level is clearly lower than what it was when it was in the boat. So the water level did drop. And the reason, probably the best reasoning for this, is that when that brick was in the boat, it was displacing its weight in water. Because water had to provide a buoyant force to keep that thing afloat. So it was displacing its weight in water. Now, it's only displacing its volume in water. You see the distinction? The volume, since this is more dense than water, its volume that it displaces is less than the volume that its weight in water would require. So basically, the buoyant force on this brick is now equal to the weight it displaces by itself, while over here, the buoyant force was equal to its weight when it was in the boat. I was hoping to see some nods and, yes, but maybe
That makes sense.
that's kind of what you thought already. Okay, but that's kind of a nice demonstration. So what I'd like to do now is go to some of those slides. And the projector controller is up here. While we're waiting for that, I have a nice little, hopefully this will show up okay on the L camera. I've got some blue beads and some white beads inside a bottle with some fluid. And what can you say about the density of those beads compared to the density of the fluid? What can be said? Yeah?
The water is a lot more dense than the beads.
The water, I'm not sure it's water. The fluid is more dense than the beads.
Yeah.
Well, if that was true, why are all the beads floating?
Oh, never mind. They're less dense.
Well, you said the water was more dense. And if the water is more dense, that would mean beads would rise. So it's clearly the beads are less dense than the fluid that's below the beads,
But more dense than the fluid above it.
but less dense than the fluid above the beads. So either that means that we've got a change in density going on here. That right there tells me it's probably not water, because water has pretty much the same density no matter what the pressure. Or it's possible we have, well, let's shake it up and see if we see something interesting going on.
I
Can you
wonder.
scoot,
Can you
can you scoot it back a little bit?
hold it up?
The white beads were at the very top and the blue beads were at the very bottom.
But now there's going to the.
Could someone provide a hypothesis as to why this is behaving the way it is? Sir?
My thoughts on it, if there is two different fluids in there that have different densities, as you shook them, they were kind of all mixed together, which allowed the beads to kind of separate. I'm not sure why they separated the way they did, but then my kind of thoughts as the fluid kind of separated back, it allowed the beads to kind of go back to where they are.
Okay, that actually sounds pretty darn reasonable. And we know that the blue beads are more dense than the white beads because when the fluid was all mixed together, the blue beads were more dense than the combined fluid, the mixed fluid. And the white beads were less dense, they floated. But as those fluids separated into a fluid that's more dense than the blue beads and a fluid that's less dense than the white beads, we then get this. So I'll take it up one more time. And Braden, what are the fluids in here?
I believe it's just super saline water.
Just regular water and heavy salt water?
Yeah.
I don't think so. I thought you mixed this up.
I didn't mix that one up. No.
Okay, it's an alcohol as well as something with salt water. But I can't remember the alcohol. Okay, but it's actually pretty interesting, but that's exactly what's going on. So Mr. Peckham?
Backwards, yeah.
Peckham, sorry. Okay, let's consider this. Oh, yeah, the question.
Oh, hold on.
Slide 4. Okay, 1 cubic foot of seawater weighs 64 pounds. God, I hate pounds and I hate feet. Suppose you pour 1 cubic foot of seawater into a plastic bag, closed with no air bubbles inside. That would be like a gallon bag. I hate gallons too. Give me liters, milliliters, grams, any day. And attach a string to it, no bubbles, lower it into the ocean. When the bag is completely submerged, how much force do you have to exert on the string to keep it up? 0, 32, 64, 128, or you in fact have to push it down. Think about this for a bit, please. Do this if you need more time. Okay, show me your cards. Okay, what's it look like on the chat?
Mostly A's, 1E it looks like.
Okay, the only choices we have that people expressed are either A, 0, or E. You have to push it down. Well, it's one of those two. It's not 32, it's not 64, it's not 128. It's either 0 or, in fact, you have to push it down. Could I get a volunteer to defend why it ought to be 0?
Yeah, I can defend that.
Please do.
So I think it's 0 because the gravity of the bag is obviously 64 pounds, and the weight underneath that has to be equal. And so it will automatically like stay there. And so the force you have to exert on it would be 0.
Okay, so you're arguing that the buoyant force is equal to its weight, so you wouldn't have to exert any additional force.
That's right.
A volunteer to defend why E ought to be right. Sir?
I chose E because the bag itself would be less dense than water, I thought, and so it would want to float. But with the water in it, it would kind of keep it right at surface level. So in order to get it fully underwater, you need to push it down.
Okay.
Cross
you-
growth.
Sorry?
Cross growth.
Cross growth. Okay. You know, I really don't think I need any discussion here because we know that plastic does float, but is the plastic really all that significant? Frankly, I'm more inclined to go with A, just because the plastic, I think, would be negligible in weight compared to 64 pounds, whatever bag we have. But if you want to be really, really picky about it, it might come into play. So you could argue for E, but my preference would be A, it's 0, just because I think that the difference in density between the plastic and the seawater is really not going to matter that much. But those are both valid reasons. Let's try the second one. So you suspend a rock now this time. Say it weighs 50 pounds and you lower it beneath the surface of the water. When the rock is fully submerged, barely right near the surface, you find you have to support less than 50 pounds because it has a buoyant force on it. As you submerge it still further, does that support force change? Is it less, the same, more? Is it exactly 128 pounds? Or do you have to push it down because it tends to float up? Think about this for a bit. So the comparison is between when it's right barely submerged, right near the surface of the water, to say maybe 20 or 30 feet down. Go ahead and show me your cards. Hey, what's it look like online?
Mix of A's and B's.
Okay, which is more?
Probably more A's.
More Golden, you said more B's?
I'd said more A's.
More A's.
More A's. Okay, A or B. Well, it's not C, D, or E. I'll just go with that. Could I get a volunteer to defend why A is correct in that you should require less force the deeper you lower this thing into the water? Anyone?
I'll have a shot at it.
Please do.
I would think it'd be less just because when you submerge something in water, it doesn't weigh as much as it does outside the water because the water kind of helps support it.
Okay, but we're comparing it to when it's already submerged to when it's just deeper submerged. Not between out of the water and in the water. That's not what we're comparing.
I would still think it as less just because density. I'm thinking how to word it properly. I think density would be stronger, slightly deeper, but not by much.
Okay, so you'd say that we'd have a greater density the deeper we go, and so therefore we wouldn't have to support as much of the weight?
Yes.
Okay, could I get a volunteer to defend B, please? Sir?
So I was thinking like an anchor on the ship. The deeper you lower it, I mean, it's, the depth doesn't really matter, I think. So I just thought an anchor on the ship doesn't have that in my mind.
Okay, what's your name, sir?
Jacob Horsley?
Okay. Well, since it's not a clear consensus, I think we need some discussion here.
So my reasoning was in the equation we came to for Archimedes' principle, the three factors were the fluid, were the density of the item, the gravity affecting it, and its area. So unless you somehow change the size or density of the rocket's buoyancy will remain the same. Or somehow lower it deep enough into the ocean to alter the gravity on it. Which I think, as you're getting closer to the Earth, would actually make it heavier.
Okay, what do we have showing up on chat?
Nothing so far.
No, nothing so far?
No.
Okay, I want to move through this. So go ahead and show me what you're thinking now after hearing some defenses and discussion.
We got one discussion.
Oh, read it out loud.
I think the pressure of the water goes up the deeper the water, which will cause the brick to be more buoyant.
Okay, well, everybody type in what you're thinking is going on now, either A or B. What's the consensus with the chat?
B.
B. Okay, B is the correct answer. The density of water does not change significantly with depth. The volume of the rock does not change with pressure. Now, if we had a chunk of styrofoam and we started lowering it several hundred meters down, the pressure would start to squish it and it would become more dense. But that's not really relevant here. We're talking about a rock and we're talking about lowering a rope. So no, you will not see any change whatsoever because water is fairly incompressible. That's why we use it in hydraulics. There is no change in the density of water unless you change its temperature or its salinity. We talked about that earlier. Archimedes' principle has nothing to do with the depth of an object in water, only on the density. So yes, if there is a change in density, that would affect it. But in the case of water, since it's so incompressible, that's just not going to occur in any body of water you're going to find. And with any reasonable length of rope you could buy in the hardware store. How's that? Okay, so I think I'll skip over, go ahead and do the next slide. I think I'll skip over this one, or maybe I'll just explain it. This is actually a bit of a tougher one, but we're kind of running out of time. A bathtub is full of ice cold water with an iceberg floating in it. When the iceberg melts, the water in the tub will do what? Well, ice is less dense than water, but not that much less dense. Because right now, because what it's floating in the form of ice is displacing its weight in water, because its weight is equal by its buoyant force. Does that make sense? So with it sitting right there floating, the buoyant force on this is equal to its weight. They have to cancel in order for it not to accelerate. So as it melts, it turns into something less dense. And when it's completely all made of water, it will displace exactly its weight in water because that's also its volume. So for that reason, as ice melts, there'll be absolutely no change in the depth of the water. It's the water level in the bathtub. It won't spill over, it won't spill out, because at any instant, as it melts, that chunk of ice is going to displace its weight in water. Does that make sense? Okay.
So its density compared to water is actually about the same.
No, that is not true. Its density is less than water in the ice form, but it's still floating. So its submerged volume is less than its whole volume.
times.
But it's because it's floating, it's displacing its weight in water at all times. And as it melts, it becomes more dense, taking up less space. But you'll always have the same fraction of ice above the water level as below the water level.
That makes sense.
So as it melts, it's turning into something in the same density as what's around it, and so the water level simply will not change. One very useful aspect of water being fairly incompressible is that if you apply a force to an enclosed chunk of water, well, that force will be transmitted equally everywhere throughout that fluid. And we can get something called a fluid lever. In fact, I mentioned this in a story I told you from my youth, where I worked in a gas station in Lowman. I was able to basically lift on a lift large trucks using pistons. So we have a narrow tube connecting to a very large tube, a large cylinder, and you've got pistons on either side. So basically the piston on the side that I would press in with a lever was about as big around as my thumb. So that's how big this was over here. And over here, it was quite large. The pistons that supported the truck were about this big around, and there were several of them. And as you apply a pressure force here, that's translated equally over here. So pretty much the same height, you're going to have the same pressure. Same pressure on either side as you push down. So if you push down with, say, a force F1 over here, you're going to get a force upwards here. Since the pressure is the same, a small area with a small force with a bigger area will give you a much bigger force. So you can get something much, much larger. So this is like a fluid lever, if you will. So if I've got a factor, say, a difference of 100 in the area, which is about what we had in those pumps, I could push down with, my whole weight, which was about 100 pounds back then.
Well, you don't have to move it 100 times as far. You can also lift something 100 times heavier.
Yes. So the work is the same. Force times distance is the same. But for 100 times the area, I could get 100 times the force. So if I pushed down with 100 pounds, that meant the force on those pistons transmitted through this was 100 times my weight. Or how many pounds? 10,000 pounds. Pretty impressive, huh? That's actually a good note to leave on. Thank you for your attention. We'll move on into a bit more gaseous topic then for Friday. Thank you for your attention.
Random